All right, everybody awake? Okay, thank you everybody for coming. Welcome to the IMA National Celebration of the Best Math Project. This usually is a pure online event, but we thought we'll celebrate also the fact that kind of everybody's close by turning this into a hybrid event. So actually there was a competition running over summer where every UK university can actually nominate one candidate for this prize, and then there is I think like 20 students or so were nominated, and then there is a bit of a competition at an online event later in summer, and we have the two winners. So the first was winner and the second was winner here, Rebecca Maver, Rebecca Sheppard. The other round, Rebecca Sheppard and Rebecca Maver. Clap. And therefore turn this into a hybrid event with the plus of not giving online talks and drinking wine afterwards, which are the first one is a much bigger plus than the second part, of course. I won't say much more because we kind of want to get started with the talks really soon, but I'd just like to invite James from the IMA to say something if he's here.
I'm here. Can you hear me okay?
Yes, absolutely.
Very good. So, thanks everyone for coming. My name is James. I'm one of the members of the Early Career Mathematicians Committee. And so I'm on behalf of the organising committee for this event. It was started by Stephen Lynch, who may or may not be here at the moment, in 2021 and during the pandemic, where he thought, let's get loads of mathematicians, loads of students to present their projects, and let's sort of make a big deal out of this and make it some massive competition and celebration. And so that did very well in the Northwest. And then last year, with the anniversary of the IMA, the 60th anniversary, we thought, okay, let's take this national. And again, that was a great success. And so we thought, let's run it again this year. And it's growing faster and faster. So please keep an eye out. We're going to be doing it again next year, roughly at similar times. But again, as Jonas said, like, big congratulations to the two winners, and what an opportunity for them to be here in the same place and to be able to present this in person. Big congratulations from us, from the ECMs and everyone sort of at the IMA. And I think with that, I would like to give it back to you. Let's listen to some fantastic maths talks.
Okay. Yes, let's do exactly that. Shall we clap for James as well? I think you can. I will just ask, because I can't see it. Andrew, are you in the online call? Andrew Hazel? No? Okay. Then I think we'll just start with Rebecca Sheppard. So Rebecca did her undergrad at Liverpool, but recently moved here to do her PhD. And she will tell us something about integer circles. And I will just put up your slides. Oh, spoiler alert, don't look. Yeah, okay. Who knows how to put this on full screen?
Full screen?
Yeah.
Yes.
All right.
That's good. So, hello. My name's, as Jonas has lovely introduced me. I just choked on my words there a bit. I'm Rebecca Sheppard. I won this competition for the University of Liverpool, but now I'm at the University of Manchester, which is here for the people attending in person. So today my talk is not usual circle, geometry on the integer grid. So, sorry, there we go. When you think about circles, you're probably picturing an object a bit like this. But that's not what I'm here to talk about today. Instead, I'm here to talk about an object which looks a little more like this. I'm thinking, how's that a circle? And that is what I'm going to introduce today. So in this presentation, I'm going to discuss geometry with integers. I'm going to discuss integer circles and their densities. And finally, I move on to intersecting integer circles and their densities. So first of all, in integer geometry, we say that two objects are the same or they're congruent if there is a lattice-preserving affine transformation or translation between them. So this is rotation, it's not rotation, it's skews, and anything that's lattice preserving, that's an affine transformation. You have skews, you have some reflections, you have some, and you have combinations of them, and you have translations as well, these preserved lattice, integer transformations. So multiplication by a matrix with integer entries and determinant 1, and translation and combinations of those. This is a bit like a sort of change of integer basis. So I put on the screen now some integer triangles. So I want you to sort of think about if these are the same or not. Well, I mentioned just the names of some properties that we have here. So we have integer length. So this is the number of integer points along an edge or within a vector. We have the integer distance, which in the case of between 2 points is the integer length, or in the case of 1.2 a line, that's the number of parallel lines going through integer points, which are included. And we have integer angles. So it's a little more complicated, but you can, people online, you can see my cursor, people in here, you can see my cursor. Unfortunately, I can't move the mouse in such a way. So people online, you'll have to sort of walk from the camera as I point, but that's like the integer angle here would be determined based on the convex hull of integer points contained within the angle. So this is called a sail, and the integer angle is defined up to sails. So this one we have just a sail 2. Between here we also have that sail, and this angle here we have this sail 1, and then you have the index of that, which is the determinant between this vector and this vector, which is 1, and you have 1 there, so that's 1, 1, 1. So for those who were having a look at my triangles, you'll find these are integer congruent. We can picture this as being, say this starts with this basis here, then this goes to this base, and this basis here, so it's 1 along that way and 1 along that way. Then this goes to 1 along that way and 1 along that way. Again, people watching online, look through the camera. There's 1 along that way and 1 along that way. Or here we have, so it's 1 that way and 1 that way. And if you think about properties which I discussed, you'll find they're all conserved here. So I'm going to go more properly into some of the definitions of those properties now. So if we let A and B be integer points, then the integer length of the segment AB is 1 less than the number of integer points which is contained within the closed segment AB. Or I suppose 1 more than the open segment, those are equivalent statements. So on this picture here, we have 4 points in the closed segment. So we say it has an integer length of 3. And the integer distance between 2 points, as I said before, is equal to the integer length of this segment. So now let's move on to integer circles. So if you think back to the start of the presentation, I shocked you with it. So an integer circle with radius r and center O is the locus of points x belonging to z squared, such that x belongs to this integer circle if and only if the integer distance between the point x and the center of the circle is equal to the radius. So here, that's the entire definition of an integer circle within z squared. And here are 2 pictures of them. So close to me, you see the picture that I showed you at the start. This is one of the Faraday sunbursts. And over there, you have just the points x which are on the integer circle. You might notice that there's more points in the picture close to me, on the left, than there are on the one on the right. Less points rather, sorry. Let's bubble up there. And that's because the picture on the right is a little more zoomed out. So if we zoom out even further, we get this image. These integer circles are not bounded. So there will be a point all the way over here somewhere which belongs to the integer circle. Sorry to people on that side of the room, because of also over here, I am more playing to this side. So informally, the density of a set A. So remember I said I'd talk about density of these integer circles, because it's not bounded, so we can't really, and it's infinite, so we can't really count the number of points or do an area of what's included in it. So we're going to talk about the density. So the density of a set A is the proportion of points in A to the points in Z squared. So that's an informal definition. We're going to need some more definitions in order to work up to a formal definition. So we say that a filtration is a set of subsets Sn, such that each set Sn is a subset of Sn plus 1. So like nested subsets. And an exhaustive filtration is filtration which satisfies that the union from n equals 1 to infinity of these sets Sn is equal to Z squared. That's an exhaustive filtration of Z squared. You could have some of other sets. That's not what I'm dealing with here. So we have a definition of density. So the density of A with respect to A, a subset of Z squared, with respect to a filtration Sn, is the limit as n goes to infinity of the number of points in the intersection of A and Sn with the number of points in Sn itself. So in this presentation, we'll be using the filtration curly I is In, is the Cartesian product of minus n to n with itself, intersected with Z squared. And we denote the density with a hash symbol, this name of the density, curly I, and of A in this case. So a way to picture what this density actually means is with this little animation. So as we get larger and larger A, we get larger and larger squares. So this square here, intersecting with Z squared, is Sn minus 1, and this one here is Sn, and these will grow to cover everything if you had infinite time, which we don't have, but that's why we consider limits. So the theorem is that the density of a unit integer circle centered at the origin, well, centered at a point O, could be anywhere, is the 1 over the sum from n equals 1 to infinity of 1 over n squared. This, from the basal problem, no, this is known to be 1 over zeta of 2. And then from the classical basal problem, we have this is 6 over pi squared. So this comes from, first of all, the lemma that the density of an integer circle of radius r is the density of a unit integer circle divided by r squared. And this sort of comes from, if you imagine you're stretching it out a bit. You're scaling it, you're stretching it that way, you're stretching it that way, you're getting r less points this way, r less points this way. So you're dividing by r squared. And then there's this other lemma, which gives that the density of the union of integer circles of radius r belonging to positive integers, centered at the same point, is 1. This is every integer point. There is an integer distance between itself and the center of the circle. So this set here, this big union, is Z squared set minus the center of the circle, which center of the circle has density 0. So this set has density 1. Combining those two lemmas, we get the formula, because we have that all of these summed is equal to 1. We do some manipulation, and we get this format, this formula here, and then the rest follows from definition of the zeta function and the Basel problem, which would be a much longer presentation than what I have time for if I explained how to get that, and it's not particularly relevant. So since this density is greater than half, we know that the density of the intersection of two integer circles is greater than 0. So having positive density means that we have an infinite, we do have an intersection, particularly this intersection has an infinite number of points, and they are laid out in such a format that they are dense in Z squared. So here is a small close-up picture. The small purple dots are points which are on the circle centered at the large purple dot, but not on the green one. Vice versa for the green dots, they are centered, they're on the circle centered here, but they're not on the purple circle. And the large black dots are points which are on both integer circles. So if you zoom out a bit, this has the green and purple dots on it as well as the black dots. So this shows the union of these integer circles. And then if we remove the green dots, this people who are viewing at home cannot see the titles of my slides because of the Zoom pop-up. Is there a way for me to dismiss this? I can move it. I've moved it. So this is the intersection of integer cycles. What happens when we move the centers? So we know we should still have positive density when we move centers. So let's see if it seems to change. So I've moved centers a bit, and we have a noticeably different shape. This shape is not integer congruent to the previous one, and neither is this gathering of points. But we see they're both, all three of these are dense, and if we sort of squint our eyes and look at them, we can guess that they have different densities. So we want the density to depend on the location of the centers of the integer circles. So if you let A and B belong to Z squared, then there exists a rational number D such that the density with respect to curly I of the intersection of unit integer circles centered at A and B is equal to D multiplied by the product for P in the prime numbers of 1 minus 2 over P squared. So this rational coefficient D only depends on the integer distance between A and B. This makes sense because that's the only thing unique about the integer segment between A and B, because everything else about it, all segments of length D are integer congruent to each other. So this is nice. It gives that this density is an integer congruency. And particularly this function D satisfies that the prime P, D of P, is P squared minus 1 over P squared minus 2. Again, for prime P, D of P to the K is equal to D of P. And then for coprime M and N, D of Mn is equal to D of M multiplied by D of N. So this gives the number theoretic property that D is a multiplicative function. So I'm going to prove this now. And I'm going to introduce you to a few tools from number theory and a tool from not number theory, which we use in the proof. So the Mobius function mu, we have that mu of 1 is 1. Mu of the product of primes P1 to Pn is minus 1 to the n. So distinct primes P1 through Pn. And mu of P to the K times by m is 0 for a prime P and some m, it could be prime or composite, and K greater than 1. So if any repeated primes in the prime factorization of D, then mu of D is 0. Otherwise, it follows this rule here. The number rise function tau, this returns the number of divisors. For the square brackets, this is some notation. If there's something in square brackets which is true, this returns 1. If there's something in square brackets which is false, this is 0. So if I had in square brackets 2 plus 2 equals 4, that would be 1. If I had in square brackets pi equals 3, that would be 0. We use variables in these generally, and big O notation. So this means that there exists a real number m, a positive real number m, such that large X, the absolute value of O of f of x is less than or equal to m times the absolute value of f of x. This is what big O notation means. So relating to the theorem from before, the density of the intersection of integer circles, S1, unit integer circles centered at A and B, is D of D times by the product of primes 1, product over prime numbers, 1 minus 2 over P squared. So I'm going to give an idea of the proof here. So we let D equals 1. This is just an example of proof. So we consider the included points in a subset of Z squared. Particularly, we're dealing with the upper quadrant up to R. So we have in square brackets summing over when the GCD of x and y is 1, multiplied by the GCD of x minus 1 and y is 1. So this gives that both statements are true. And this greatest common divisor function relates to integer length between the segment, or integer distance between 2 points. The greatest common divisor of the x coordinate and the y coordinate, change in x and change in y, is the integer distance. So then this is equal to, doing a lot of number theory, the sum over when D1 and D2 belong to the intersection of the interval 1 to R intersect with Z, and the greatest common divisor of d1 and d2 are 1 of r times by mu of d1 d2 over d1 squared d2 squared plus o r log squared r. So we take the limit as r goes to infinity and we divide by r squared. So it's the number of points we have. Get that the density of the integer circle with respect to curly I is the sum from d equals 1 to infinity, summed over the sum for when d1 and d2 product to d, and the greatest common divisor of d1 and d2 is 1 of mu of d over d. This simplifies to be the sum from d equals 1 to infinity of mu of d tau of d over d squared. So we write this as product of prime numbers. This is 1, the product for p and the prime numbers of 1 plus mu of p tau of p over p squared plus mu of p squared tau of p squared over p to the 4, and so on. We just write these terms here, these d's, as the prime factorizations to get to here. Remember that mu of p to the k for k greater than 1 is 0, so all of these terms here disappear. So we just have the sum for p belonging to the prime numbers of 1 plus mu of p tau of p over p squared. We know what mu of p is. Particularly mu of p is -1, and we know that tau of p is 2. So -1 times 2 is -2. So that gives the formula for the product for p belonging to p squared of 1 minus 2 over p squared. And for d greater than 1, we follow a similar proof. It was a very similar thing for when p was a prime number and power of prime, and we used product things to do with multiplicativity to get the when d is a composite number. So in this project, I've studied a few things. I've studied notions of density and integer geometry. I've studied the densities of integer circles, and I've studied the intersections of integer circles. So a few further questions would include, so is density a geometric invariant? So this further question, there's a bit of work on this already, which says that, yes, it is geometric invariant. In fact, we can do better than that for shapes of a particular property, basing around the density. If were the boundary grows linearly and the area grows quadratically, we have a mixture hold, then obviously any integer transformation of this curly I filtration. Sorry if you're watching online, I hope you can read the board, I'm drawing. We have there's an integer transformation from this to say this. This is the same as doing an integer transformation of this to this. We have that these densities are the same. So taking this density of this is the same. So then taking this square density of this with this transformed in the sort of opposite way would also be a nice integer invariant. We're interested in what the properties of this product for p belonging to the prime numbers of 1 minus 2 divided by p squared. And we're interested in the density of the intersection of integer n spheres. We're also, I don't think this is on the slide, interested in what happens when there's more than 2 circles. So when there's 3 circles, we always have the positive density. For greater than 3 circles, there is an article which shows that sometimes we don't really have existence of the intersection. We have that the intersection is the empty set. And then for integer n spheres, the definition of integer n sphere is very similar to the definition of an integer circle, just to a higher dimension. So the definition of the integer length is still the same, and this is still analogous to the greatest common divisor. And then the definition of an integer n sphere is the same, just in zk rather than z2. And we actually find that this formula here has an interesting relation to cases other than 2 integer circles. So we have 1 minus 2 over p squared with some coefficient with 2 integer circles. So if you have k integer circles, allowing d to sometimes be 0, we would have k here, so long as k is not equal to p squared for any p. And if we change the dimension to integer n spheres, we'd have the dimension here be n. Again, k cannot be equal to p to the n, otherwise you have something invalid in this expression, but by omitting that term from the product, we get something similar to that. So I've got some references here which are interesting for further reading about the subject. So the first one here is currently it's accepted by Arnold Mathematical Journal. That's out of date. It is published in Arnold Mathematical Journal, so you can read it now. It's also on the archive. This deals with the case I sort of just described about multiple integer circles, but more so about existence and about the different radii that they can have, rather than. So that's triangle. So it'd be how many of these do we have and what radii do we have for them? It's interesting. It follows to do with greatest common divisors of the integer lengths of the sides, with triangles, well, with shapes in general, and with things like squares. Sometimes we don't have any intersection of integer circles. So the square with vertices here, and here. This square does not have a circumscribed circle. Here, circumscribed circle is an integer circle which goes through all of these points. And that's interesting. Then there's Geometry of New Attractions by Oleg Karpenkov. This is a good book to get to grips with basics of integer geometry. There's J.W. Castle's An Introduction to the Geometry of Numbers. Again, that's sort of foundational text relating to geometry of numbers, not in this sense, but it's useful, interesting to read. And there's proofs in the book, and that has a proof for the Basel problem in it, which gives why it's 6 over pi squared instead of just 1 over z for 2, which we wouldn't otherwise necessarily know. So thank you all for giving me a few minutes of your time today. If you have any questions, that includes people online or people in the room, I'm happy to take them.
Yeah, that was a brilliant talk. Thank you so much. Indeed, are there any questions in the room or online? Person in the room? Is it easier? Okay, maybe I can do an icebreaker question. So what is your favorite integer geometrical object? Is it a circle, or is there another one you're even more excited by?
Well, circles are where I've done most of my research, so I'm quite excited about them. But I'm moving on to do some research into the broken lines in integer geometry, and there's very little sort of research in this area, but we're looking at sort of having an integer invariant analog to properties of differential geometry here. So we're looking at introducing an integer invariant notion of curvature, tangents, and normals. Additionally, I find integer angles are quite interesting. So I'll remove this broken line, which I didn't need to draw, and I'll instead draw a nice integer angle. So I spoke a bit about these, but since we've got a lattice here, I'm not fully drawing one out, but you'll have the convex hull of the points which are included in this. So this will be a convex shape, so there's no integer points between here and here. And these are completely invariant on the choice of this lattice here, or this sail here it's called. So if there is an SL Z2Z transformation from this to another angle, it will have the same sail. If an angle has the same sail, there will be an SL2Z transformation from this to this. And quite interestingly, there is not a unique way to add these angles to each other. And I'm doing some research into how I would bisect these. And this relates to another analog of circles being equal distance from lines rather than equal distance from points.
Okay.
Any questions about the other objects I introduced today? I'm also willing to take questions on.
So you said that people are interested about the properties of that sum with the one.
The product.
Yeah. What properties are people interested? Like to learn?
Well, what I'm interested in them, just how does it relate to different integer geometric properties? Is there an expression for it in terms of an integer geometric property of a circle that I've not mentioned today? Is there a particular it tends to be expressed in terms of a known irrational number? We know it's irrational, but can it be expressed in terms of like pi or something like that? F of pi. I mean, yes, but can it be a rational expression in terms of known irrational numbers? And again, another thing that was interesting is how it generalizes to multiple integer circles and the higher dimensional case, which I already discussed, that we do know now that the numerator changes based on the number of integer circles, and the denominator, the power of the denominator, changes depending on the dimension.
Okay.
Are there any applications of integer circles?
This is quite a new area of pure math, so there's not currently any applications, but I imagine they could maybe be used relating to encryption of something, and it's possible that there's a way to compute, not necessarily using integer geometry, but using integer circles, but definitely using integer geometry, because we have a lovely relationship to continued fractions, which have very good application in terms, again, these angles. This relates to a continued fraction here, so if you have A, B, C, and then the index of these, A1, B1, why did I call them that? I don't know. But this relates to the A continued fraction, A1, B, B1, C. And this is, for those not familiar with continued fractions, 1 plus 1 over A add 1 over A1 plus 1 over B plus, and so on. And this is the best way to approximate an irrational number as a rational number. And it's obviously this is a rational number if it converges, but if it doesn't reach this line, if it is infinite, then cutting it off at any point is the best way to approximate an irrational number, based on Diophantine equations and such, and not Diophantine approximations, which is from number theory. So this relationship with continued fractions means there's probably some computational link somewhere between integer geometry and its applications, computers potentially.
Okay. So I think if there are any more questions, we'll have some party afterwards. So please wait until then. But let's clap once more.
Actually, I'll check, see if anyone's put anything in the chat, because you can have a chat on.
Yeah, no,
Zoom.
that's fine.
No one's put anything in the chat.
Yeah.
Okay.
Notice, notice. Okay.
Thank you.
Thank you so much. So let me just try to. Okay, should work. Okay, and our second speaker is Rebecca Maver from University of Manchester. Yeah, please.
Okay. So, thank you for everyone that's attending online and in person. My name is Rebecca Maver, and this presentation is a section from my third-year undergraduate project, which was finite difference methods for solving convection diffusion equations. So before we get started, I wanted to say thank you to the team at Manchester for nominating me for this competition, and of course the IMA for selecting me for a prize. It's really exciting to be able to do this. And also thank you to Jonas Latz, who organised a lot of things for me on the Manchester end of stuff. So let's get into it. This is a brief overview of what I'm going to try and do today. I'm going to explain to you what a convection diffusion equation is. I'm then going to explain a specific type of numerical method that we can apply to these equations to get approximate solutions. We're then going to briefly analyse these methods and evaluate their performance with some experiments. And hopefully by the end, we will have a nice framework that you'll be able to apply to lots of different equations of this type. So, fundamentally, convection and diffusion describe how a quantity is transported. So, convection is motion due to force. We might imagine atmospheric particles in a wind, or in this picture, we have heat being transported by the circulation of water. Whereas diffusion is movement from high to low concentration. So that's that kind of more like natural spreading out effect of particles or heat being transferred by a warmer area touching a colder one. And often these two phenomena are happening in tandem. They're happening at the same time, and we can model their combination by a partial differential equation, as with lots of different physical processes. So this is a specific problem I'm going to be considering today. We can see here we have the second order derivative in space, which is the diffusive term. And then we have this convective term where W there is just a constant which represents the strength of that wind force that I was just discussing. We also have a time derivative because I want to see how this system will evolve in time. We don't have any source term on the right-hand side there, so nothing is being added into our system. And we're considering just a one-dimensional interval domain with some boundary conditions and initial conditions to go along with it. To kind of give you a mental picture of what this problem could represent, we might imagine like a metal rod that's filled with air, and the endpoints are kept cold. And then we heat it up to some initial uniform temperature distribution 1. And then we want to track how this temperature distribution changes through time, subject to diffusion and convection. So we actually do have an exact solution for this problem, which is given here. And that's kind of nice for us because we can compare directly how well our numerical approximations do. As you can see, even for a relatively simple version of the equation that we have, the exact solution is not kind of trivial to get to. And if we added any additional complexities, we would find it very difficult. And there's quite a few problems that actually don't have exact solutions, but we are able to apply the numerical method that we're going to develop today. And that's what makes it really useful. And that's what we're going to do now. So the first step is to discretize our domain. So transform that continuous interval into n equally spaced grid points of width h. And then the idea is that we find approximations to our quantity u at each of these grid points xj throughout time. And we can store each of the approximations at these points in this vector fold u. So now we've discretized the domain, we can do a similar thing with the spatial derivatives. And this is what finite difference methods allow us to do. They approximate our derivatives by taking a sum. And this is kind of a very natural way to approximate derivatives, which if you remember when you're first introduced to them, we kind of think of it as a change in y divided by change in x. And it's a similar thing happening here. This diagram shows us that the gradient of the red line, it shows us an example of the center finite difference method, where the gradient of the red line is our approximation to the gradient of the blue line, which is the exact derivative at that blue point. Now, there's lots of different finite difference methods that we could choose from, and all of which have some kind of clever combination of u at the point xj and the surrounding points. And these can be derived, and we can calculate their remainder terms by taking Taylor series expansion around u at the point xj. And here I have the centered finite difference methods for the first and second order derivatives, which both have a remainder term of h squared, and these are the ones that I'm going to be using today. And just to quickly note, we actually always know the exact solution of u at the endpoints. So that's u subscript naught and u subscript n. And that's because they are prescribed to us by the boundary conditions. So we're only really interested in approximating the interior points here. So substituting these finite difference approximations into our partial differential equation, we've eliminated that spatial derivative and reduced it down to n-1 ODEs in time. So that's 1 ODE for each of those interior grid points. And we can express these all at the same time using this matrix, where B is a coefficient matrix here, and we have our boundary conditions and initial conditions stated as well. So that's really nice. We've gone from a PDE to an ODE, but I want to get this into a linear algebraic equation that we can solve more quickly. And to do that, I want to approximate the time derivative with a scheme that will allow me to step forward discretely in time. And there's lots of different ways that we can do this as well. But I'm going to be using what's called the Crank-Nicholson method today, which approximates the time derivative by taking an average of the function evaluated at time step n and n+1. Now, this scheme is quite widely used. It has some nice properties. And it was also co-created by Phyllis Nicholson, who was a female mathematician here at Manchester. I think it's the computer room downstairs in this building that's named after her. So there's a little biography if you're interested. But she worked on problems for the Ministry of Supply during the war. She's, and I always like to shout out whenever a female mathematician pops up. So the way we derive this scheme is we can think of it as taking the value of the function at a mid-step. So that's that purple dot there. And using a Taylor series expansion in a very similar way, we end up with this expression where we can see that delta t here is the size of the discrete time step that we're taking, and we have a remainder term that's order delta t squared. So applied to our ODE system, we arrive at this time stepping scheme, where you can see we've approximated the time derivative with this difference here, and we've evaluated this term at the average between time step n and n+1. We can then rearrange this to get this nice linear algebraic equation where we can very clearly see how we get from time step n to n+1 subject to this initial condition. So that's great. We've gone from our partial differential equation to a linear algebraic equation that can be solved very easily in something like MATLAB. And this gives us access to approximate solutions at all of our grid points for any time step. But of course, these are fundamentally still approximations, and we want to have some idea whether they're any good. And in order to do that, we can look at the error that will inevitably be there. So the first kind to consider is the local truncation error. And this is what's left over when we substitute our exact solution, so the one that satisfied our PDE, into the numerical method. Now, when we do that for our problem, we get remainders that are order h squared and order delta t squared. So what we can say is that our scheme is consistent order 2 in space and time. And this is really nice because it means if we make our spatial mesh really fine, so we let h go to 0, and we take very small time steps, so delta t goes to 0, then this local truncation error will also go to 0. And it will do so quite quickly because we have this second order dependence. The next quantity to consider is the global error. And this is kind of more intuitive version of the error that we're used to. So what we can define is the error vector, which says, okay, we have access to our exact solution. Let's find out what it is at each of our grid points and at some specific time tau, and directly compare it to our what our approximations say. And then we can calculate the size of this error vector by taking the mesh dependent L2 norm. Now, the reason why I've defined this is so that we have some notion of convergence. And we say a finite difference solution converges to the exact solution at some time tau if the size of that global error vector goes to 0 as delta t and h goes to 0. So this is a very important property because it lets us know that if we make those parameters delta t and h sufficiently small enough, we will be getting to our exact solution. So we have some idea of how far away it will be. And we can also prove that if a scheme has this property, then it will converge at least the same order, so the same rate, as the local truncation error. So in our case, that was that second order dependence. So another notion to consider is that of the stability of this. So this measures how close the approximate solution remains to the exact solution, and just the extent to which local errors accumulate. So oftentimes instabilities manifest themselves as our approximate solution oscillating around our exact solution. And this can happen if our mesh size is too coarse, so h is too large, or our time step size is too big. So we end up shooting off far away from our exact solution with our approximations, and we can't ever really get that. So this means that we often need upper bounds on these parameters. For the specific choices that I've made, we do need an upper bound on the spatial mesh size h, so that needs to be relatively small. But because the Crank-Nicholson method is implicit, which means that it uses information from the n plus 1 time step at each stage, there are actually no bounds on the size of the time step delta t. So we can take any size. And this means the Crank-Nicholson method is unconditionally stable. So all of that is nicely summarized by this theorem, which says that a consistent finite difference formula, so one in which the local truncation error goes to 0, is convergent, so the global error goes to 0 if and only if it is stable. So our local errors don't accumulate over time. And that means we can conclude about our scheme that we've built today and the choices that I've made, that for any small mesh size h and any time step delta t, our choices should be stable and therefore converge to the exact solution at this second order brings. And this is really nice to have in our back pocket. We've now kind of backed up the choices that we've made today. And we know that we're going to be able to get really close to our exact solution. But of course, this is still theoretical analysis, and it's important to back this up with some numerical experiments. I'm going to do some now. The first experiment I'm going to show you is a little simulation of exactly the scheme that we've built up with these specific parameters. So a wind strength of 10. And we have our exact solution as this blue line, and our red stars are our approximations at every grid point. Now you can see it does a pretty good job in the middle, but at the edges, we have these kind of strange oscillations, quite extreme actually, and that's maybe surprising because that kind of goes against the stability properties that we were just discussing. Not only are we far away from the exact solution, but we're actually negative. And that's concerning because we can tell from our exact solution that our solution shouldn't actually never be negative, it's often 0. And if we think back to our metal rod, it's like saying that the edges will suddenly become very cold, much colder than the surroundings it's in, which we know that's not how those physical phenomena work. So not only are they far away from the exact solution, but they're what we call unphysical. So we basically just need to throw out these approximations, which is not ideal. So I'm going to propose that the reason for this is that the analysis that we were doing was on the PDE and that operator, but it didn't consider the problem as a whole, which is to include the boundary and initial conditions. And this leads me to the idea of well-posedness. So a problem is well posed if its initial and boundary data are unique and continuous. And if we look back to the ones that we had for our problem, that is definitely not the case. At t = 0, we have this big jump from 1 down to 0. So our problem is not well posed. And just to kind of back up, kind of prove to you that I think this is a good explanation, I'm going to show you an example of a very similar equation that is well posed. So you can see everything starts at 0 here, it's nice and continuous, using the exact same techniques that we used for the other problem. And our red stars, that you can barely see them, they do a pretty good job of approximating the blue line. And this is more what we were expecting to happen. So this is actually a feature of the Crank-Nicholson method, those oscillations. And a kind of intuitive way to think about it is that we are taking an average. So if the value at time step t0 is vastly different from t1, then that average kind of throws it in the wrong direction and doesn't have much to do with the exact solution. So in order to try and soften this, to dampen these oscillations, I'm going to employ a fully implicit method for that first discontinuous step. And this is called the implicit Euler method. And you can see that I've replaced this average with just the value of u at time step n+1. Now, the reason I wasn't using this method from the very beginning is because it has a larger truncation error than the Crank-Nicholson method. So it will converge to the exact solution more slowly. But this leads me to my second experiment, which is the exact same parameters and problem as before, but using the fully implicit method for the first time step, and then switching back to Crank-Nicholson afterwards. And you can see that we have really softened those oscillations, which is great to see. But unfortunately, we still did dip into the negative numbers, which we know cannot be in a reliable approximation. So I'm going to try using the fully implicit Euler method for the first 2 time steps and then switching back to the Crank-Nicholson to see if that fully gets rid of our problem. And it does. We no longer have any negative solutions popping up in our approximations, but we might have had to sacrifice some accuracy in the middle section there. So I mentioned that these two methods have different convergence properties. So in order to kind of quantify whether using a combination of the two has helped or hindered the convergence of these numerical schemes, we can look at some global error data. Now, if you recall, the global error was just taking the difference between the exact solution and our approximations and finding the size of that. So this table is related to that very first experiment that I showed you, the one with the extreme oscillations. And if you recall, we would anticipate the Crank-Nicholson method to converge second order in time. And how that would manifest itself is this final column being a pretty constant number. And this clearly is not the case for this set of data. So we know that those boundary and initial conditions have actually really harmed the convergence properties of the Crank-Nicholson method. But by just using that first fully implicit step, we've kind of restored that second order convergence again. You see we have a relatively constant number in that final column there. And this is not that badly harmed by using two implicit steps. It's perhaps less clear cut, but it's still definitely better than the data from that very first experiment. So to kind of round that section out, this is not the only way to deal with those oscillations, and it might not be ideal in every circumstance. You know, if you're particularly worried about those negative solutions, this might not be the most reliable way. What you could do instead is add a bunch more points at either end to try and dampen the oscillations. You could smooth out the boundary and initial data to kind of force it to be well posed. Like lots of different ideas there. But I hope that this investigation kind of demonstrates how boundary and initial conditions can have significant impacts on the performance of a scheme. And by thoroughly considering this example, we have developed a framework that we can apply and adapt to much more complicated versions of the convection diffusion equation, like in this simulation here, that don't have analytical exact solutions. So, you know, it's very useful for things like that. And that's the end of my talk. And here's a couple of references if you're interested in this topic. But thank you very much for listening today.
Yes, Rebecca.
In the example you gave, applying the Euler method twice managed to eliminate the oscillation and the negative values. Would it always be eliminated after 2 steps of the Euler method, or would you need to?
I
Yes.
think that's no. Sorry, I was just
Sorry.
acknowledging. Yeah.
It's fine.
No, that's a really good question. I think that's kind of what I was saying about the reliability factor. I think it would depend. It would depend a lot on it. It might, well, I don't know exactly, but it might depend on how sharp the profile is. Might depend on the profile. It would depend maybe on the number of points you had on your spatial domain. So I think that's the good point about it. It's like you would have to check, you know, every time, depending on what problem you had, what specific equation you had. So it wouldn't just be, okay, you've done 2, now it's done. That was for a specific problem. So that would be the thing you'd have to check.
Yeah. Could you I know you don't necessarily know, but do you think there would be a way to, and I'll put you on the spot a bit here, sorry, if you'd rather not say, that's fine. Would there maybe be a way for you to guess how many times you'd need to do the Euler, or find an upper bound on the amount of times you'd need to do the Euler method based on the problem itself without actually trying it?
I think you might be able to do that if you from what I would approach it from, I think you would have to you could code it in. So you'd code it in that it would check whether you got any negative solutions, and then it would run it again. So that's how I would think of doing it. I don't know if you'd be able to do it before, maybe you would, that would be cool. But how I would probably think of doing it is you run the first few time steps. Okay, you got a negative solution, let's start again, add an implicit Euler step. And so do it more kind of experimentally, I suppose. Yeah.
Yes.
You mentioned how before that why the distance method wasn't as effective is because the boundary conditions are unphysical. Go from the like being a value of 1 to 0, and t suddenly gets slightly above the dot, and t is not 0 anymore. You then use the implicit Euler method to correct that. Why did you not look at changing the boundary conditions to sort of suit them to be more physical?
So the boundary conditions themselves are physical. So the thing that was unphysical was the negative numbers. So those could be boundary and initial conditions that are physically possible. But I think that's a good point, kind of what I was saying at the end, is in one way to change it would be kind of smoothing them out and, you know, using like a curve, like a steep curve. So it would be like a continuous function rather than like a kind of step, if that's what you're meaning. So I think that would be what you have to do. Does that answer your question?
Yes.
Yeah.
Thank you.
Okay, are there any more questions? So chat, but I think there's more questions. So Neil Palmer, thanks to both, and congratulations to both. And sorry, okay, you can read it later. I think James has his hand up. No, he's clapping. Okay. So have you, because obviously this problem could appear also in kind of like weird, like strange domains, where you sort of say, okay, kind of due to like being like weird corners or so. Have you looked, aside from kind of square domains, also other domains? No. That's a big answer to a big question. Yes. Okay. Are there any other questions? Okay, then let's clap again. So
am I leaving the stage?
yes, you can leave the stage. Okay, no, so thank you all for coming, the people in person, people online. It was a pleasure to have you here. Now the people that are here can now kind of go outside and drink some wine. The people online hopefully have kind of supplies at home to celebrate by themselves or with their friends. Yeah, thank you all for coming, and hope to see you next year.